That's fine. We're good to go.
Good to go?
Yep.
Okay. Thank you all for coming. I am very pleased and happy to introduce my collaborator and friend, Anna-Lena Deppenmeier, who comes to us from NCAR. And I got her PhD in climate science from Wageningen University in the Netherlands in collaboration with the Royal Netherlands Meteorological Institute, also known as KNMI. From there, she went for a postdoc at National Center for Atmospheric Research, where we met, working on a pre-field campaign for the TPOS project. TPOS is Tropical Pacific Observing System. I can remember TPOS, right? So that was for her postdoc, and since then she was promoted to a project scientist position to lead that pre-field campaign at NCAR. We also work on marine heat waves together, and she works on one of my favorite things, water mass transformation, so I think we've had a lot of fun conversations over the course of the day, and I'm looking forward to hearing about the cold tongue and what sustains it. So take away, Anna. Thanks so much.
Thank you, Liz. Okay, I think people can hear me, at least I can hear the microphone, so that should work. Thank you so much for the introduction. Thanks to everyone who's here. I'm noticing now that I talked to a bunch of you, and I kind of want to talk to all the rest of you, so maybe after we can have a quick chat about what you do. But now, yeah, the floor is mine to talk for a little while. Troubleshooting?
It was a little loud.
It was a little loud? Okay, yeah, we don't want to overwhelm.
That's good now.
Okay, thanks. Yeah, so Liz already mentioned I work a lot on the Tropical Pacific Observing System, and I want to tell you a bit later on what a pre-field campaign is. So that's Tropical Pacific, right there in the name. And we've had conversations about water mass transformation, so I use water mass transformation techniques and analysis in my work, and I'm also going to get into that more. But if you think about a water mass transformation, it means you change the properties of a water parcel, right? And in my case, I'm asking the question, how does the cold tongue stay cold? So that tells you about what kind of water mass transformation I'm looking at, and that's in temperature space. So I'm going to be looking at what processes take up heat into the ocean and change the water temperature of a parcel. And I kind of, got ahead of myself. I already said this, but that's the outline of the research questions of my talk. We're going to start with how is upwelling related to heat uptake, and I'm just going to give you like a little bit of a preview. If you have the tropical Pacific, you have the trade winds blowing there, and this is going to be said again in a couple of slides, but I hear that it's better to tell people things several times, and it's also good for me to say things several times. Then you have Coriolis, which sort of diverts the water parcels that are driven by these trade winds into a direction away from the equator, which means that water is being taken away from the equator and needs to be replenished from below, so that's upwelling. So that's kind of the typical upwelling system that people usually think about in the tropical Pacific. And I'm going to be talking about how is this process related to heat uptake. Then I'm going to be asking the question, I want to be looking at that in the mean state, but also how does this vary interannually? And when we think about the tropical Pacific, we think immediately ENSO, Niño Southern Oscillation. So that's the ENSO time series here that you can see. And how does upwelling and water mass transformation vary with ENSO? What is the seasonal impact? And we have subseasonal timescales. I'm going to be talking about something called tropical instability waves, so hence the little wave symbol here, and how that varies upwelling and water mass transformation. And if we have the time, I've been very ambitious and included some results on wind-driven upwelling, which is exactly kind of what I've talked about here, but just on the surface layer and not so much in the depth. Then I'm going to talk about that too, but we might run out of time, so if you're interested, then we can maybe chat after. Okay, so now we're going to zoom back out, and I just wanted to make sure we're all on one page. We all know where we're, I don't know. I look at the tropics all the time, but you might not. So we're talking about the tropical Pacific, which is kind of like this region, and most of the results I'm going to show you are in this box. The tool, well, the data model output, the observationalists really don't like it when you call model output data. The model output that I'm going to be using is 5 daily, so fairly high temporal resolution, 10-kilometer gridded global ocean model output. So I'm showing you some sea surface temperature here in this temporal resolution, and you can hardly see it, but there's kind of these like gray lines on there, and the gray lines are the grid. So just to show you that we're fairly well resolved in this region. And now I just wanted to give us a second to have a look at this this little feature that's happening right here. So this is the tropical Pacific, the equatorial zone, and we see this typical behavior. Well, now it's of course not typical, now we're getting ENSO. Yeah, so we usually have colder temperatures in the east, warmer temperatures in the west, and then, yeah, this is like a couple of years. So you really see this western warm pole here extending to the east. This is like a really big ENSO happening here right now. It retreats, we get these cold features of the tropical stability waves emanating from the right, and I just wanted to give you an impression, like that's the sort of variability that's happening here. We have this really kind of fine scale variability here, and then you can clearly see a basin-wide variability as well, right? You see this western warm pole now here, it's going to come right up and extend again, and so that's the ENSO variability. So the region is fairly complex in that sense, is that, you know, we have all these different temporal and spatial timescales that we need to be taking into account. So now before we get deeper into the ocean, haha, very funny pun, we're going to actually dive into the ocean along the equator. So we're going to look at a cross section along the equator, which I've sort of drawn here. So this is the east, this is the west of the equatorial Pacific, and this is the surface, and this is the thermocline. So the thermocline, you know, is like the sharp gradient of temperature. We have a shallow thermocline in the east, which means cold water from below, kind of closer to the surface and deeper in the west. And along this thermocline flows one of the strongest currents in the world. This equatorial undercurrent goes up to 1.5 meters a second. It's a really strong current. And on top, oh, okay, well, apparently I chose to do this first. So we have cold temperatures in the east and warm temperatures in the west. Usually this is also what you've seen just now. This is a sea surface temperature gradient that, you know, helps the trade winds. That's why I included this now. So we got strong trade winds, partially, you know, due to the sea surface temperature gradient, and that introduces a south equatorial current, a current that flows opposite to the direction of the equatorial undercurrent. So we have a region with really a lot of shear, and that's going to be important later on. But so you can already see, like, something's flowing to the east, something else is flowing to the west, and, you know, at some point this basin is bound here by the east. There's going to be South America on this side. So we usually think of this as a circulation, right, that goes kind of in this direction. So something's going to connect the subsurface to the surface. And that's where people then say this is this equatorial upwelling that happens. Equatorial upwelling, and that's what I want to talk about. And this is, I've drawn a really big arrow, but it's a very small velocity compared to the velocity of the equatorial undercurrent and the south equatorial current. So this upwelling, because it's a small number, it's hard to measure in situ. So people say that upwelling is such an important point, but we have a hard time measuring it. So if we look at observational estimates from all the way back from 2000s, we have this upwelling of this estimate of upwelling, which the equatorial undercurrent is about here, maybe all the way in the east it's here, but this is an estimate over a really big box. That's the only way that people can get to estimates of upwelling. And then this is another estimate that is from 15 years earlier, and another estimate, and they kind of look a little similar, but there's like this really strong difference of it actually becoming negative in one of the estimates. So we don't really know what this upwelling structure looks like, and if we now put error bars that's on the last estimate, we see that we really don't have a good idea of the estimate. So you see the error bars span all the way from 100 meters span negative to positive, so you really don't know very well about what this upwelling looks like. And that's kind of where I come in with my pre-field campaign project. So one of the things that we want to do is better constrain this upwelling, better understand the processes behind it, and we want to be going out and measuring it. And we're going to use model output to find out where can we best measure which variables that will tell us about this upwelling. Okay, so that's just a little bit of a background of upwelling. Is kind of like a complicated concept to measure in the tropical Pacific. And then the other point about upwelling is that people just draw this arrow kind of here across the thermocline, but that implies that there's a change of heat or a water mass transformation happening from a parcel that sits here to here, right? Because they have different temperatures. So part of the upwelling in the tropical Pacific is going to arise just from the fact that the equatorial undercurrent goes in this direction, which is a vector that has an eastward component and an upward component, right? So there's a part of the upwelling that is just a parcel that sits here that sort of goes slightly to the right and slightly up, doesn't change its temperature actually, but just changes its location in the z coordinate, and this is what we call the adiabatic upwelling. But the thing that really matters so this could transport temperature of this water class all the way over here, right? But it doesn't really actually do anything to the surface temperature, right? It just moves the water parcel along its thermocline, like along its isotherm. But when people draw the upwelling arrow, they always draw this. So something has to happen that has to take up heat, that has to change the temperature of this parcel to get up here. So that's why I keep saying, like, what keeps the cold tongue cold? Where is the heat going? What is the process that's taking the heat from the surface and putting it into the ocean and thereby transforming this water class? So that's something, that's what I call the diabatic upwelling. You're going to hear me say that a lot. And that's the process that I really want to be focusing on, although I also do compare the diabatic to the adiabatic really briefly. Okay, a little bit more background, and that's that we have two different ways of measuring this diabatic component of the upwelling, again, which is related to the heat uptake, which is kind of the climatic important feature here. So we want to be tackling it from several sides. We have a kinematic equation, which is really just divergence in temperature coordinates. So this looks kind of scary, but what it means is we have a WCI plus that goes along the across the upper isotherm. CI is cross isothermal. That's equivalent with diabatic upwelling, and I apologize for that. That's just the hole I dug myself by giving these things the names. And the minus here is just the one on the lower isotherm. And what we would be determining is the divergence. Yeah, okay, I said that. And how we would determine is by divergence. Sort of, if we make a box out of this isotherm, you can just say I slice it from 140 west to 120 west, and I'm looking at my isotherm structure, and I look at what flows out of the isotherm in this direction. This is the divergence in temperature coordinates, and then it also takes into account the movement of the isotherm, which doesn't lead to cross-isothermal velocity because it's just an expansion of the isotherm. That's a way to diagnose this diabatic upwelling. And why is that relevant? That's relevant because if you've heard of ENSO, you've probably heard of warm water volume. That's the volume of water that sits above the 20 degrees Celsius isotherm. So again, we have the east of the basin here, the west here, surface, and this is the 20 degrees Celsius isotherm, which is just a measure of the thermocline, really. And so how this is varied by processes, going out of the sites, but also by processes from above, and that's this diabatic upwelling. So the diabatic upwelling that we can determine through this kinematic estimate gives us a warm water volume change, and that's really relevant because what I'm plotting here is warm water volume in the dark color and Niño 3.4 index in the red color, and you can already see with just a blink of an eye that those are correlated, right? So the warm water volume leads the Niño 3.4 index, and the Niño 3.4 index is a sea surface temperature index in the tropical Pacific that tells us whether there's an El Niño or a La Niña. And if that is up here, then this is the axis for the red line. So if the red line is really high, we have a really big El Niño, and you can see that that is preceded by this warm water volume anomaly. So this diabatic upwelling has an impact on the warm water volume, and that can then be used to predict, forecast, let people know ENSO is coming, right? And we want to be able to measure this quantity to better constrain the warm water volume so that we can, improve our ENSO forecasts. And this is just sort of a proof of point. As I told you, you could see that these are correlated. These are now the correlations between warm water volume and sea surface temperature, and then I've done them in green here for the entire basin, so the entire tropical Pacific, and in blue is the eastern part of the tropical Pacific, which is where the thermocline is shallower. So you can see that, especially if you're looking in this region where there's the Niño 3.4 index, there's a really high correlation with a lead of 3 months. You have a lower correlation, but out to 6 months if you consider the entire basin. So this is a really useful thing for us to know if we want to forecast ENSO. Okay, so that's the kinematic estimate of the warm water volume budget. And what we would do is we would go out and measure temperature structures and see how the temperature structures change and velocity, and say, okay, this is the divergence or convergence in this temperature, so this is a way that we could go out and measure this. But then that's basically a diagnostic, right? So we can see how much does my warm water volume change due to temperature divergence and convergence. But something that I'm really interested in is what causes this change in the warm water volume? What causes these diabatic velocities that change the warm water volume? And I know I'm showing a lot of equations, but there's more equations that connect the previous equation to this equation, so you're just gonna have to take my word for it that the diabatic upwelling that you diagnose from the kinematic estimate is the same as the upwelling that you can get through from the heat budget. And that is really cool because, okay, I have to take a step back again. So on the left-hand side is just the total temperature change divided by the magnitude of the temperature gradient. And what that means in physical words is we're taking the temperature gradient, which is indicated here, and we're projecting the motion into the direction of the temperature gradient. Right? That's what we want because we want to get to the cross-isothermal velocity. We're taking into account the change of the isotherms, like I showed you just before, right? If the isotherm moves and my water parcel moves, I'm still not getting any cross-isothermal, right? So I need to have them relative to each other. So that's where this term is coming from. And I can connect this to the heat budget. And the cool thing about that is that now I have these individual physical processes that I can say drive this diabatic upwelling. So I can not only say, well, this is the diabatic upwelling that leads to warm water volume change, which is relevant to ENSO. I can also say it is solar penetration that contributes to this. It is the vertical mixing that contributes to this. Horizontal mixing and the covariance term, I left a little no icon for the horizontal mixing because it's not very relevant in this high resolution model. But you can maybe remember the solar penetration, the vertical mixing, the covariance term. And then there's a higher order term here that arises due to the averaging that we do because we don't have instantaneous fields, it's 5 daily fields. You can get an estimate of how big this is from how well your budget closes, and I can tell you it's like completely irrelevant. It's even less than the horizontal mixing term. Okay, so we're gonna use 36 years of this high resolution ocean model output that I've just shown you a video of. We have the full heat budget, so we don't need to be doing residuals, which means that I can tell you that this higher order term is small because otherwise it would have been folded into the residual, but I can tell you that it's very small. I'm not validating the runs here. You just have to take my word from it that the equatorial undercurrent is pretty good and the temperature structure is pretty good, and you can see that in my papers if you really want to. Okay, so this is something I already said before. The kinematic and the thermodynamic estimates, they're the same, so it's two different methods to get at the same thing. So the overall big dream, and this is probably not a next year dream, but maybe a career goal, is that if we get a good grasp on how these interplay, we can measure velocity in isothermal coordinates and get to mixing or get to solar penetration, right? So it's all about what can we learn about the ocean from things that we have are readily available. We have readily available instruments that can measure those. And I've been talking a lot, so I'm going to skip this slide. It's just comparing the two on different averaging timescales, but we're just going to not worry about it. If you want me to show you, I can show you later. Okay, so let's get to some results. So the diabatic upwelling, again, is this process that takes up heat, changes the temperature of the water parcel, and thereby, transports heat into the deeper ocean. What does it look like in the 36-year mean? So one thing to maybe think about is that when I showed you the W estimates earlier, these total upwelling estimates, people do these over really big boxes. This is from 180 east to the coast of South America. So it's just along the equator, and it's really only from 3 north to 3 south. This big average that people do is over 5 south to 5 north, because you need certain assumptions to be true, which don't really hold close to the equator, so people do this over the really big box. The cool thing that we can see here now from this diagnostic is that this diabatic upwelling really isn't happening equally over this box. It's very narrow on the equator and really located on the cold tongue. I should have overlaid use of temperature contours here, but if you look at the mean cold tongue, mean temperature structure in the tropical Pacific, It's like a cold tongue here and then it gets warm here. So you can really see that this diabatic upwelling, which is highly relevant to ocean heat uptake, is happening in this really narrow strip on the equator that we need to understand better. And then there's one thing that I've been kind of hinting at, but hiding a little bit from you, is that I put here 22 degrees Celsius. That's because when you do a water mass transformation in temperature, it doesn't really make a whole lot of sense to look at a meter depth, because this meter depth is going to have different isotherms moving up and down, so you would just kind of dilute your signal. So the way that we look at this diabatic upwelling is in temperature space. So if I now take these lines here, which are coinciding with the tau line, so we have moorings here. So at some point I'm going to get around to validating this as much as I can, that's why I chose these locations, but it's just to give you a little bit of an idea of what the cold tongue structure looks like. The y-axis now is temperature. So this is an isothermal coordinate. The hatching is whenever this isotherm doesn't exist for less than 50%, because you don't have 30 degrees Celsius in the cold tongue location ever, but you sometimes have 25 degrees Celsius. So basically, when something is really close to this hatching, we're really close to the surface. And so what you can see is that this kind of interesting structure is really close to the equator. You can see that also if you look in the vertical or in the temperature coordinate. This is the same x-axis here is the y-axis here, so it's really the same sort of slice. And you can see that when we are all the way out here in the west, in the cold tongue, we get very shallow diabatic upwelling. It's really close to the surface, so it's really only kind of close to where the hatching is, and it only gets down into the ocean a little bit. And then if we go further east, it gets down into the thermocline. And that's where it's interesting, because again, that's where the change in temperature, the heat uptake, gets taken up into the ocean. It doesn't just stay in the surface, but it goes into the ocean, potentially being taken into the equatorial undercurrent, right? And that water parcel is then kind of zipped away, taking the heat with it and transporting it elsewhere over the world. Yes?
Quick question, how can you tell that that's the thermocline?
Well, from this you can tell. What you do is you look at the temperature structure. So I just showed you this line, right? So I would make that plot with isotherms and see where is the biggest temperature gradient, dt, dz. And so I'm showing here 22 Celsius. I'm showing you 22 Celsius here. But some people would use 20 degrees Celsius for the thermocline. In this region, it doesn't really matter as long as you have a big temperature gradient. Does that get to your question?
Yeah.
And that's kind of also, that's a good question, and that's why I'm showing you the vertical cross sections, is that it doesn't completely depend on which temperature you choose, right? As long as you don't go to 12 degrees Celsius, which is like arguably way below the thermocline anyway, you're gonna get a similar signal whether you're at 22 or at 20 degrees Celsius. So that's my measure for the thermocline. At another location, I actually used the average over 20 to 22 Celsius because I wanted to be accurate, but you get the same results, basically. Yeah, and so this interesting thing is that, again, we are interested in where this diabatic upwelling happens in the thermocline, because again, that's where the heat uptake is really going to reach the global ocean. And so that doesn't happen all that much at 155 west, right? That really happens at 125, 110 west. So you could argue it kind of starts at 140 because you see it getting stronger here in the 22 Celsius degrees isotherm close to the thermocline. But it's really like the action is sort of further in the east. I think that's all I wanted to say here. No, so I wanted to point out one more thing, and that's I call this diabatic upwelling as if it's a W, an upward velocity, which is true as long as the temperature gradient is into the vertical, right? As long as the isotherms are staggered like this with what it is in the thermocline. But when we get to the mixed layer, the isotherms are actually vertical, right? We have the cold tongues, it's cold here and warmer here. So if I was to look at upwelling really close next to the surface, it's actually more of a meridional direction. So that's another reason why I'm choosing to focus on the thermoclines, because that's where I can best equate this diabatic upwelling with an actual vertical motion. Okay, so this is I didn't tell you how I diagnosed this, but this was diagnosed from the thermodynamic estimate. You get the exact same when you do the kinematic estimate, because again, they should be the same thing, as long as you're not really close to the equator, where again, this, to the surface, sorry, where you get this directional difference. But this is just one part of the story. The interesting thing, like I said, was to now use the heat budget and compute the individual components from the heat budget and look at what processes make up this diabatic upwelling. And so this is basically the same figure that I've just shown you, just at 140 west now for a variety. So it's in temperature space. Now we go from 5 south to 5 north, and we see the total diabatic upwelling. So that's the very left-hand side of the long equation that I showed you. These parts here are calculated according to the heat budget, to the right-hand side of the equation, right? So these are not calculated the same way. They come from different parts of the equation. The vertical mixing component here is due to the dJ, J is the turbulent heat flux, dZ. So you see that there's two different signs here, and that's, when I explain that in a second, that's because we take the vertical derivative, right? It's not just the total heat flux, it's the vertical derivative of the heat flux. And then we have a strong contribution from solar penetration. And I showed you earlier that there's a horizontal mixing contribution and a covariance or eddy contribution, which I'm not showing you here just because they're really small, because if you add the two of them, you get this sign. So these two are not calculated the same way. This is the left-hand side of the equation, and this is the right-hand side of just these two terms. So we have now attributed that this diabatic upwelling, this water mass transformation in the tropical Pacific, is really due to the solar penetration contribution, which plays a large role at the surface, which makes sense, right? Because solar penetration decays rapidly as you go into the ocean, and the vertical mixing contribution, which is really the key one that drives this thermocline water mass transformation, this uptake of heat. And I've just said a lot of words, so I thought I'd show you some nice little drawings to show you this process again. So if we looked at the same region, this is again 0, north, this is the south or the north, so we're looking at the same as those cross-sections that I just showed you. These are the isotherms. We have the equatorial undercurrent sitting here. I didn't draw the south equatorial current, but it sits on top and it opposes, right? It opposes the equatorial undercurrent. And that introduces the shear, which gives rise to a lot of mixing. So these blue swirls here are the mixing. And then we have solar penetration coming in at the top, and I tried to sort of show you that there's lots of it at the very top, and then there's less below because it decays quite rapidly. So if we look at typical profiles of heat fluxes going into the ocean due to solar penetration and turbulent mixing, they look like this. But because we're interested in water mass transformation, so we're not interested in the total heat flux, because the total heat flux doesn't really matter for heating something. What matters is the difference between what goes in through the top and what goes out through the bottom, right? That's what heats that layer. So that's d flux dz. So those are the profiles that what they look like here. And if you add these two components, then you get this kind of structure. This is what we, from understanding of our processes, what we would expect the diabatic upwelling to look like. And again, to visualize this is we have a water parcel here sitting between the 20 and 21 or 22 degrees Celsius isotherm. There's some heat coming in here and some going out, but there remains some heat here, which means that this water parcel is moving up in temperature class and in vertical space, upwelling, causing this diabatic upwelling. And one last reminder that this is upwelling really strictly only when you're in the thermocline, so when you're in this stratified region of the ocean. Okay, so how does that work out? This is the structure that we expect from the vertical mixing and the turbulent heat flux and the solar heat flux component, and this is the structure that we get in the mean from this 36 years of model simulation. So that works out pretty well. Another thing to note here is that this is the diabatic upwelling in meters per day, and this is the total upwelling in meters per day. So this vector that I showed you before, right, that there's a part of it going to the east and a part of it going up, that's the decomposition of this vector. You can see that the diabatic upwelling is about a third of the total upwelling, so it's not the majority, but it's a significant contributor to vertical motion in the thermocline. Okay, so that was in the mean. Now we want to be looking at how does this vary on the different timescales. Now I'm showing you again the same pictures, temperature space here, latitude here, and the neutral is kind of very close to what you've all just seen. That's this V-shaped structure with the water mass transformation penetrating the surface, the thermocline only on the equator. And now you can see that during El Nino, there's really hardly any water mass transformation happening, while during La Niña, the signal is really much stronger. And that's kind of interesting in itself, because when we talk about El Nino and La Niña, we usually think of ENSO as kind of like the big disruptor and the one that has kind of the big impacts. And maybe this is also disruptive because it's not taking up more heat into the ocean, but really La Niña is the one that's doing all the work. She's taking up the heat into the ocean and distributing it in terms of buoyancy flux all over the world. So La Niña is sort of, from this point of view, the more important contributor. And then we want to see, do the balance of these physical processes still hold for the different modes of variability? And we can see here again the vertical mixing contribution and the solar penetration contribution. And I mean, you can already see that the balance looks very similar as what we've seen before. And it's really the vertical mixing is the one that modifies the thermocline heat uptake also on the La Niña and El Nino timescales. Okay, so then we wanted to look at what is the seasonal cycle here. This is where I now do like another average of the thermocline. I take 20 to 24 degrees Celsius again, doesn't really matter. We wanted to look at what does this look like through the seasonal cycle. We have this narrow band of upwelling, though you can see that before it kind of looked like it was really only in this like 2 degrees north or south of the equator, maybe 1.5 degrees. You can see that there's times of the year where this diabatic upwelling is more spread out, specifically to the north. There's more of it, like more action to the north here, some more action to the south here. And then there's some regions when, some time of the year when it's really narrowly confined. And so we can be looking at why that is, what modifies this seasonal variability of diabatic upwelling. And so for that, I'm going to be looking again at these like 3 points on the equator, and I'm going to look at the vertical components, so into the isotherm coordinates again. And so this is the diabatic upwelling now in a sort of seasonal sense with the water column. And I'm showing you all 3 here. Maybe we just focus on one because that's easier to follow. So you can see that there's diabatic upwelling really happening throughout the year, which is kind of interesting because let me see if I can, how can I go back? Just, oh, I can't. Haha. Because I should have pointed out here is that it's not only narrow here, right, the diabatic upwelling, but it also looks like there's very little of it happening. So it looks like maybe we have a similar like shutdown, similar to what we have during El Nino in the seasonal cycle as well. But if we look at the vertically resolved, we can see what there's a little bit of a reduction in diabatic upwelling here, but we really have it throughout the entire year. And what I'm also showing you here in sort of hidden is again the processes that make up this diabatic upwelling, and that is in dotted lines. I'm plotting the solar penetration when it exceeds a threshold, 0.3 meters a day. It doesn't matter if you use 0.2, it's a fairly steep function. So this is a big contribution of solar penetration, and the dashed lines are a big contribution of vertical mixing. And so these kind of really follow especially the maxima, right? This maximum here is quite clearly only driven by the vertical mixing, and you can see the solar penetration sitting on top. Whereas here earlier in the year, we have a little bit of a mix, and it's much closer to the surface again. So maybe this is more of a off-equatorial water mass transformation rather than this diabatic upwelling. And to confirm that, what drives this vertical mixing is, I have, I don't know, like 10 million plots of different indicators of what drives vertical mixing, but mainly it's, I've already said this, the shear. So the shear that is between the equatorial undercurrent and the south equatorial current is what drives this vertical mixing. So what I'm showing you here is the total shear, and you can see that where there's a big change in shear, there's a big change in dg/dz. So again, we need to look at the change because it's the vertical derivative. And so this change in the vertical shear is what drives this vertical mixing driven diabatic upwelling here. And this is to, I've been saying this a lot now, but this is to remind us that this is what the sea surface temperature stratification looks like. So if we look at early in the year here, where we have around 25 degrees Celsius, this peak here, that overlaps with the solar penetration, we're really in this warm region here in the water column. So we're not in the stratified region. So this is not where this diabatic upwelling is strictly the cross isothermal velocity, but not upwelling because it points off away from the equator. Okay, so the seasonal cycle follows sort of the same laws and the same processes as we see in the interannual variability. Now I want to look at these tropical instability waves features that we've looked at in the video before. So a way to look at tropical instability waves, other than just looking at a video, is we look at a Hoffman model. So we look along the equator here, and with the year goes on as we go upwards. And so we see this warm sea surface temperature here, warm sea surface temperature here, seasonal cooling, and then these streaks here indicate the tropical instability waves that bring cold water along the equator westward. And that's also indicated here by these black lines, which are tropical instability wave kinetic energy. So that's kind of a test, you know, like you can see the streak here, and then it's coinciding with the high instance of tropical instability wave kinetic energy. So these are the tropical instability wave kinetic energies. Tropical instability waves passing through. They also quite clearly have an impact on diabatic upwelling. You can see that there are these streaks here that coincide with these streaks in the sea surface temperature. You can also see a seasonal modulation of the diabatic upwelling here, where we have no tropical instability waves, but we also just have warm temperatures here, and we have hardly any diabatic upwelling on this side. So now, is this again the same? Is this all vertical mixing driven and solar penetration driven? You might. So this is now on the equator, where we see this. We can see in one blink of an eye that these signals are very similar. This is the covariance. Covariance is interesting because when we have a tropical instability wave passing, it changes the temperature structure, but it also changes the velocity structure. So this covariance term really says how does the temperature get modified at the same time as the velocity. So it's an indicator for the tropical instability wave. Often people call this eddy. This is the eddy flux, but then when I say eddy, sometimes people think of something else than the tropical instability waves, which are more like a coherent, sort of always the same looking feature. So that's why I call this covariance. But you can think of it as an eddy flux too, right? So on the equator, we again have the same balance of vertical mixing contributing to the diabatic upwelling. But if we now go to 2 north, where we are sort of outside of the immediate impact of the equatorial undercurrent, which again induces this shear, which is the main driver for the vertical mixing, we can see that the balance looks different now. So we can again see tropical instability waves passing by. We see these streaks here in the total diabatic upwelling. And now the signal here looks something like the total signal. The vertical mixing signal looks something like the total signal, but the one that gets closer, or it has a bigger contribution than on the equator, is this eddy flux, this tropical instability wave covariance-induced diabatic upwelling. So this is interesting because we now have a regime change, right? We have a change from this really purely vertical mixing-driven diabatic upwelling to this feature moving by that brings diabatic upwelling as well. And if we compare the tropical instability waves, so we are looking at isotherm space and diabatic upwelling for phases of high tropical instability waves or low instability wave, diabatic upwelling, we can see that this induces a difference in the total diabatic upwelling or heat uptake into the ocean that is similar in size to that during ENSO. So La Niña has more diabatic upwelling than El Niño, and high tropical instability wave has more diabatic upwelling than low. So these different timescales in the seasonal cycle is similar on magnitude. Let's not look at that because it just confuses us. But basically the interesting thing here is that I tried to, when I showed you the video, maybe I should have pointed it out more, but I tried to show you that there were these like tropical instability wave features usually whenever the ENSO, the warm pool was retreating, right? So we are in this cold period when there's lots of tropical instability waves. So there's a relation between when there are tropical instability waves and when there's El Niño and La Niña. And so the thought here is that there's more tropical instability wave during La Niña, which this modifies the diabatic upwelling, right? So could these smallish, shortish scale features, 15 to 40 days and like 1,000 kilometers compared to ENSO, which is a 2 to 7 year variability, could this variability in the diabatic upwelling maybe be related to the occurrence of tropical instability waves? And that's something that I wish I could tell you the answer to right now, but that's something I'm trying to still work on. What is the scale interaction here? Is it that the tropical instability wave really have a rectifying effect on the El Niño Southern Oscillation signal? And that would be really interesting because tropical instability waves need to be resolved. They're relatively small scale features, and not all our climate models are doing a great job at resolving those. So I'm arguing that the tropical instability waves here really show you that we need either a parameterization for that, or we need to make sure that our models are getting the heat transport related to them. Okay, so this brings me to sort of the conclusion of this part. The diabatic upwelling, which takes up heat into the ocean, is mostly vertical mixing and solar penetration driven. But if you look off the equator where you have a regime shift from this really strongly sheared region, you see the tropical instability waves playing a really large role. All timescales, the seasonal cycle, the El Niño Southern Oscillation, and the tropical instability waves have variability that is sizable, and nothing can be neglected. So this is kind of telling me when I go out and measure this thing, I really want to make sure I sample tropical instability waves, the seasonal cycle, and ideally the El Niño Southern Oscillation. So this is where I was going to tell you a little bit more about this field campaign. So like I said, I'm working on a pre-field campaign, which is kind of a cool thing because instead of just identifying a process that we are interested in, we're identifying processes in the models that we have representation of, but that we think might be flawed. And little hint, vertical mixing might be one of those, right? It's parameterized. We don't have a whole lot of benchmark observations. And we're saying it's really important for the global circulation. It's really important for heat uptake into the ocean. So we need to go out and measure it more. And we are trying to figure out how can we do that. And this gets kind of a little bit back together again to what I was talking about in the beginning, where we have these two approaches, right? The kinematic approach and the vertical mix, the heat budget approach. So if we can constrain both of them in an intensive field campaign at the same time, we can learn what we can learn from the kinematic about the vertical mixing and vice versa. So we're now working on the TPEX, the Tropical Pacific, the TPOS, Equatorial Pacific Experiment. Pacific is in there twice, but TPEX just sounded better, I don't know. So we're gonna have one campaign that's really, this is the region that I've been basically showing you most of the time. What's in the background here are surface temperature anomalies, and they're actually current, and you might all know that there's a big El Niño coming. You can really see it right here. It's on the rise. And yeah, we want to be measuring this in this region, and what we'll be doing in the near future is we'll be doing a lot of these experiments where we go into our model model output and subsample the model output in a way that a field campaign would be subsampling. So you put sort of virtual moorings in different locations, then you try to get to the divergence, then you try to get to diabatic upwelling, then you try to compute the things that we have the full solution for from this subset of information, and we can see what can we learn if we implement this array, or if we implement this array. And there's a lot of opportunity for some cool playing around that I'm personally really excited about. That you can put little fake floats in the ocean and put little gliders, and this is going to be a lot of fun. Okay, and this is where I end, because the next thing is about the wind turbine of the upwelling, and I don't think we have space for that. So, thank you.
Okay, let's start with the student question. Evan.
For the observational campaign, are you also going to look at the Argo floats and other current observational products that are available there?
Yeah. So basically so the TPOS is the Tropical Pacific Observing System, which includes moorings. I don't think I have a figure. Like it's a moored array on the equator, but also off the equator, but it doesn't only include the moorings. Argo is considered part of the Tropical Pacific Observing System. And of course, because moorings they're really great because they're time series. So you can, with some other information, you can see like tropical stability waves coming by, you can see ENSO sloshing back and forth, but you only have 1 point information, right? So what we're going to be trying is a combination of moorings, Argo flows, whatever we can have, but the timescales I will say are a bit tricky, right? Because it's like monthly, on the order of monthly, but for these tropical stability waves, you might want higher frequency. So we'll also be using wave gliders, which I don't know if you've heard of those. I just recently learned of them. They're so cool. They're like these things that are glide on the top of the ocean, and then they have this second layer, and sort of the way that the waves introduce a difference in distance between these two components. They manage to move forwards, so they can like hold. I put this array away, but like we could put wave gliders in this formation, and they could give us information about like the moorings are just here, right? But then we could span these the sides of the triangle volume, for example, with these wave gliders. So we're going to be making use of everything we can get our hands on, with moored arrays, moorings kind of being the main part, just because there's already a line of moorings. You can see that here, like in the black one. So we have some context to interpret the new results, and that's important in a dynamic region.
And great talk, very interesting. I have a very basic and naive question, which reading the title makes me think that if there's diabatic upwelling happening, is there a chance that there could be downwelling happening in that region, or that's not just physical?
So in this region, yeah, I'm kicking myself a little bit. I used to have these figures of. Let me just quickly scroll. Do I have this? No. Okay, so that diabatic downwelling, what would that mean? That would mean temperature changes in the other direction, right? So you go from warmer to colder, so you lose temperature. So where do you think on the planet would that play a role? Where you lose temperature and you lose heat and you move something down. That is where you have, water mass formation in the high latitudes where you drive the Ultra-intensity gradient. So that is a possibility, but not in the tropical Pacific. The tropical Pacific is actually this is a pretty cool, pretty interesting region, and I should have shown you this. So if you look at tropical instability waves, let me just show you the tropical instability wave. I lost my cursor, I can't. So imagine a tropical instability wave, which is like, it goes this way. And so what happens, you have cold temperatures, right? So when you have cold temperatures in the ocean, what do you expect your surface heat fluxes to look like? You usually expect outgoing surface heat flux, right? Cooling, because usually you think of like incoming surface heat flux is warmer surface temperature. In this region, it's the opposite. Coinciding with these cold features, you have an excess amount of heat going into the ocean, which is why this is so interesting, because the heat that goes in doesn't heat the surface, right? Because it coincides with these cold surface temperatures. This diabatic upwelling, this water mass transformation, allows that heat to really go into the ocean. And there's a paper by Ryan Holmes that shows that the heat that's going into the tropical Pacific in this region by this mechanism really supplies buoyancy to the global circulation. And I should have shown you that, I kept saying that, but so there's, this region is special in that sense, is that we have heat coming in, which is really like transported right, into the ocean. It doesn't stay in the mixed layer, it doesn't warm the sea surface, it gets transported into the ocean. Does that answer your question?
Question before Evan, there's another question. You go.
Okay. I have two questions about the field campaign preparation, especially about this slide. How do you make a different design, and when you make the design, how do you benchmark them using the model?
Yeah, so the different designs, the way that we come up with the original? That's the first part of the question, right? Like how do you come up with these formation? So the black, the sort of grayish squares here in the back are moorings that already exist. So a big role that no one really wants to think about is money. A field campaign costs lots of money, and putting moorings in the ocean costs lots of money. If you already have a line that has moorings, what you want to do is you want to use that, right? You want to make use of that and capitalize the money and effort that's already put in. So that's our number one consideration, not number one, but it's the first step in the consideration is that we have these assets out there. Then we think, what can we do based on this line that will let us estimate scale interactions? I've been talking about the scale interactions in the sense of that tropical instability waves are fairly small scale, and then ENSO is the bigger scale, right? So we want to make an array that spans scales, and especially we want to get off the equator because the one measurement of vertical mixing that we have is right here, right on the equator. We have nothing anywhere north, we just have it on the equator. So we want to learn this image that I showed earlier about the, moving north, the Hofmüller, right? You could clearly see how the eddies there have a big effect. Like we want to see, is that true? Is that what we can measure? So therefore we need to put something up north. So this is our second step, is that there are some moorings there, we can put some measurements, some mixing meters there on top. And then what we want to do is we want to get to volumes, because we want to say, if I take the measurement right here, what does that say about a location up here? There's recent mounting evidence that turbulence, which drives this diabatic upwelling, right, is organized in coherent scales. So it's not just completely random. And like I showed you with the map of diabatic upwelling, it's not just equal all over, the equatorial Pacific. There's places and times when it happens. And this is associated with large-scale variability. So what we want to do is we want to learn, what can we learn from this location about this location and this location? And so the arrays that we form will give us some spatial information, and then because we want to get to the kinematic, which is a divergence, so you need information about the boxes, we will have like nested boxes. So that's this reasoning. You can do nested boxes as well with triangle shapes. And then you don't need 4 points, but you need only 3 points at the site. So this is like, again, sort of an economic, can we do more with less moorings? But there are other factors playing a role because the currents go sort of in this direction. So maybe it's easier to estimate what flows through here and here than what flows sort of, diagonally through here. So that's what we consider. And then what we do to validate if this is a good setup is we use a model that has resolved time and space scales of what we want to measure, and we know the divergence or the diabatic upwelling, whichever quantity, in this box, right? Because we can take it from the model and we average. And then we calculate what do we get if we just have these 3 points of information. Do we get the same value? And that is often not the case because you're going to be making assumptions. You don't really know. If you don't know this line, you might be missing like a filament, something. So what we want to see is what is the array that makes us beat down the noise compared to the signal. Did that make sense?
Evan.
So you had those plots where you showed the vertical mixing as broken down by the seasonal cycle, and during April the vertical mixing was extremely constrained just to the equator, but it was still happening pretty strongly.
Right.
And you showed off the equator that the covariance was playing a bigger role in the mixing off the equator during that same season.
Right.
So I guess what I'm wondering is, like, does the strength of the equatorial current itself stay the same throughout the year, and it's just that it can't spread latitudinally, or like does it get stronger and weaker throughout the season?
Yeah, that's a good question. So the equatorial undercurrent varies throughout the year and is actually weakest in spring. So that is when we will have reduced shear. So when I don't know why I can't find my. Let me see if I can.
It's up on the screen, so maybe try sliding to the side a little
Oh,
bit.
there you go. To which side?
Go to left.
Yep, it's here. Okay, great. Okay. So here you can see this clear seasonal variability, right? This is on the equator. So you see sort of a lack of diabatic upwelling here, which is really correlated to, in the interannual sense, and here is there's not a shutdown, but a relaxing in the trade winds, which relaxes the south equatorial current, which reduces the shear, and also relaxes the pressure gradient that ultimately drives the equatorial undercurrent. So both of those relax. You have less shear, you have less diabatic upwelling. So the variability of the equatorial undercurrent plays a role here. And then I forgot what was the
I guess like what is constraining, because you still had vertical mixing right along the equator, but not off of the equator in your other plots. And so I was wondering what was causing the constraint specifically.
So you mean this versus this?
It was farther back because it was
Okay.
just along the equator. It was the seasonal cycle plots. Yeah, this. So you still have.
Well, you have
diabatic
very
upwelling.
little here, right?
Yeah.
So you have very little diabatic upwelling here. And that was, again, I showed you sort of an average over this thermocline region, right?
Mhm.
Which I took to be this region. And so what you're seeing there is really this upper limb of the diabatic upwelling,
Okay.
which now it's, again, like a sort of dug ourselves a grave here by calling this diabatic upwelling, which it really isn't, because this is motion of equatorial in the mixed layer, so it's not strictly upwelling anymore.
Okay.
And you can see that there is some shear, but it's really high up in the water column. So this is, the balance changes. You get less shear, you get less vertical mixing induced diabatic upwelling, and the signal is then dominated by the solar penetration.
Okay.
And that was kind of the solar penetration that it plays such a big role in diabatic upwelling. And again, diabatic upwelling is related to heat uptake, was kind of a big deal. Like people usually don't consider explicit solar penetration. And this is kind of saying, yeah, you really want to look at the budget of heat uptake.
So you have a slowdown during the season in a seasonal cycle sense.
Yeah.
Is an ENSO event like
Yeah.
a failure to restart in that case, basically, or?
It's not, that doesn't work with the seasonality, but
Yeah.
an ENSO event, what happens in an ENSO event is that we have less of this sea surface temperature gradient, right? We have warmer temperatures in the east than we usually have.
Mhm.
So we have less of the circulation, which is the same as the trade winds relaxing.
Yeah.
So it's not necessarily a continuation and a failure to start, but it is a relaxation of the winds,
Mhm.
which leads to less surface current and less undercurrent. And so in my first paper on this, I looked at because the diabatic upwelling is a dz, so a vertical derivative of the turbulent heat flux, which has to do with mixing, which has to do with the temperature gradient as well, right? It's a diffusivity times the temperature gradient, and the temperature gradient also changes during ENSO. And so that I looked into it, it's really the shear component so the relaxation of the equatorial undercurrent that drives this change.
Okay.
So it's kind of what you said, I think. I'm just reminding myself that it's exactly what you said.
I want to think about that.
Yeah.
We'll talk later.
Unless we have one more really quick question. See no hands, we'll call it a day. Thank you again, Anna.
Thank you.